Hello friends, welcome. We are dealing with the experiments related to operational amplifier and linear integrated circuits. Today we will be discussing about the filters. We have some elements like R and C. By using that we can remove unwanted portion of the signal. But due to the problem associated with the passive filters, that is, unless ZL is much larger than XC1, the load is likely to affect the performance of the filter. Hence, we are moving to the modification in the filter and we arrived with the term active filters. In these filters, we are using active element like operational amplifiers. Today, we will be dealing with classification of these active filters, namely low pass filter, high pass filter and band pass filter. We'll connect the circuit on the breadboard and we'll verify the output waveform. Let us start with the low pass filters. As the name itself says, the filter which passes the low frequencies and blocks the higher frequencies will be called as a low pass filter. You can see in the frequency response that until the frequency FC, that is cutoff frequency, is reached, the signal is passed, and when it is beyond FC, the signal starts decreasing. The output, or you can say the gain of the circuit, starts decreasing. Now I have marked here as minus 3 dB, and that is nothing but when XC1 value is exactly equal to the resistance value. So we have a gain equation for the filter as XC1 divided by under square root R1 square plus XC1 square. Now if we check at lower frequencies, the XC1 value will be very much higher, as XC is nothing but 1 divided by 2 pi FC. At lower frequencies, XC value will be higher. So for this higher value, higher than resistance value, what happens? The gain equation is nearly equal to 1. So at low frequencies, the gain of the circuit is almost constant at 1. But as you go on increasing the frequency, the XC1 decreases. And at a point when XC1 and R1 value are same, there will be decrement in the gain. Okay, we call it as attenuation in the signal. Now this is marked as the 3 dB less than minus 3 dB output voltage, and the frequency at which the gain of the filter is minus 3 dB than the maximum value, we call it as a cutoff frequency. So when we connect this circuit, we will note 4 parameters, namely frequency, output voltage. We'll calculate voltage, output voltage divided by input voltage, that is the gain, and we'll convert that gain into decibel, so that it is easy for us to draw the response of low pass filter. Similarly, next thing, the high pass filter, not much difference there, but what happens? A high pass filter blocks the low frequency and it allows the high frequency to flow. Now I'll draw the circuit by modifying the same LPF. If I interchange the capacitor with the resistor at input side, it is nothing but a high pass filter. So this is the circuit diagram for high pass filter. You can just see here the capacitor and resistor from the previous circuit, those are interchanged, and now this is the high pass filter. Now when we discuss at lower frequencies, the XC1 value is very much lesser than the resistance value. Hence there will not be any output. You can say there will be zero attenuation at the output. At higher frequencies, what happens? XC1 is it goes on increasing, and the circuit voltage, that is the circuit voltage gain, sorry, it is reaching the value of 1, you can see here. And the frequency when the output is 3 dB less than the maximum value, we are calling it as a cutoff frequency FC. At FC, we must note that the gain value will be 1 divided by root 2, that is 0.707 times of the maximum value. In other words, it is minus 3 dB less. As we discussed, two types of the active filters, low pass and high pass filter. One is allowing the lower frequencies, blocking the higher frequencies. Other allowing the higher frequencies and blocking the lower frequencies. Now what I'll do, I'll make use of one LPF and a HPF, and those are connected back to back. Input is connected to a low pass filter, output of low pass filter is connected to high pass filter, and now I'll checking what is the output of that particular circuit. And when I draw the frequency response, I arrive with this. Say I have a cutoff frequency for LPF as 100 kHz and FC for HPF is 10 kHz. Then what happens? The LPF starts working first. This is drawn here. So it starts from here and it is at 100 kHz, that is FC value, it starts decreasing. So minus 3 dB. This I'll call it as a F2, or it is a value. For example, it is 100 kHz. Similarly, the output, this signal is given to the HPF. What is HPF? It blocks the lower frequencies and allows the higher frequencies. Lower frequencies than what? Than FC. So it is marking the 10 kHz here, and below this all the signals are blocked and it is only allowing this. And the resultant is the low frequency range and high frequency range are blocked. Only the frequencies in between F1 to F2 are passed, and remaining all the frequencies are blocked. Hence the name band pass filter. Band is nothing but it is a group of frequency, say from F1 to F2. Pass in the sense it is passing only this block and it is acting as a filter. So the name band pass filter. One more filter is there. It is called as a band reject filter, where it is rejecting the specified range and allowing the remaining things, remaining frequencies. Now we will connect all these three circuits on the breadboard and we will note down the frequency, output voltage, we will calculate the gain and gain in decibel, then we will try to draw the frequency response of LPF, HPF and BPF. So this is the circuit of LPF connected on the breadboard. You can see at pin number 3 we have one capacitor and a resistor. Sorry, pin number 3 is connected one capacitor to the ground, one resistor, and to that input is applied through the signal generator. So we are using a signal generator to apply the input at pin number 3. At pin number 2 we have two resistors. One is between pin number 2 to ground and pin number 2 to pin number 6. Only this is the connection. For biasing the operation amplifier, we are making use of dual power supply. A positive 12 volt is applied to pin number 7, negative 12 volt is given to pin number 4, and common is given at ground of the breadboard. At pin number 6 we have connected the DSO, or you can use the CRO. On CRO you can see a sine wave. So on the signal generator we have applied around 327 Hertz of the frequency and voltage of around 2 volt peak to peak. Okay, for this input we will be checking what is the output, and I have pressed here measure, and it will I have selected V peak to peak on the first value. So I'll be noting down only these values. If you are using a CRO, you just check what is your volts per division, and according to that you will calculate what is the voltage value at the output. Okay, now what is the procedure is, I'll go on increasing the frequency on the signal generator from 300 to around 1 megahertz, and I'll verify what is the output voltage. Okay, so I'll note down at 300 hertz the voltage here is around 3.80 volts. Okay, I'll increase the frequency to 500 hertz. Okay, it is around a little bit more than 500. Okay, for that 500 frequency I have the voltage of 3.76 of voltage. Again I'll be changing the frequency to 1 kilohertz. So it is around 1.1k, and you can see the output voltage as 3.20 volts. Okay, again I'll be increasing the frequency to 2 kilohertz. So for 2 kilohertz the voltage is 2.56 voltage. Similarly, I'll be go on increasing the frequency, and I'll note down the output voltage each time. So these are the sample readings. For LPF. We have calculated the output divided by input, that is the gain of the circuit, and that is converted into decibels. Now using these values, I'll be drawing the frequency response of the filter. This will be your typical low pass filter frequency response. I hope you have used the Semilog paper. Like graph paper, it is not equally divided, but it is 10 times. It is 1, 2, 3 up to 10, then it is 100, then 1000, 1k, 10k, 20k, and so on. So for all those frequencies I have noted what is the gain value. I have joined all the points to get this frequency response. Similarly, this is the next one, the connection for high pass filter. As I told, I have just interchanged this resistance and the capacitance, and the resultant is a high pass filter. The procedure remains the same. I will set the frequency on the signal generator, and each time I will be noting the output voltage using your CRO or DSO. So at first you can note here at 1 kilohertz of frequency the output voltage is around 1.32 volts. I'll increase the frequency to a higher value, say it is 2 kilohertz. For 2 kilohertz the output voltage is around 1.84 volts. Okay. Similarly, for 5 kilohertz of frequency, you can see here the output voltage is around 2.48 volts. Okay. Similarly, I'll go on incrementing the frequency, and each time I'll be noting what is the output voltage. So these frequency values will be go on incrementing, and after one point the voltage gain will be constant. Okay, so it is exactly opposite to low pass filter what we studied. So this is the frequency response of high pass filter. You can see the lower frequencies are blocked. After FC, the gain is attaining the value of 1. Similarly, when you design a band pass filter and connect it on a breadboard, the frequency response for that will be approximately like this. Thank you.